However, we physicists say that the universe was created in a Big Bang 13.7 billion years ago. But then the question is, why did it bang? What set off the bang? We don't know. It's a big mystery.
In the vast expanse of space, as the James Webb Telescope reached its peak of functionality, whispers of anticipation spread among scientists and stargazers alike. Little did they know that beyond the realm of their expectations, a revelation of breathtaking proportions awaited. Brace yourself for an extraordinary account, for the lens of this celestial sentinel has pierced the veil of the unknown, revealing a startling truth. The very fabric of the universe, that cosmic tapestry woven across eternity, might be nothing more than a single, unimaginable atom. What does this profound discovery entail, and how does it revolutionize our understanding of the vast cosmos? Join us as we unveil the enigma unfurled by the James Webb Space Telescope, a discovery that holds the power to reshape our perception of the cosmos itself. Unveiling the secrets of the universe is an awe-inspiring endeavor. But what if we told you that amidst its grandeur lies a connection to the tiniest building blocks of matter? The vast expanse of the universe intertwines intriguingly with the minuscule atom. Consider, for instance, our solar system, an unlikely parallel that may seem preposterous yet finds support in scientific discourse. In 1913, Niels Bohr drew inspiration from the solar system to propose an early atom model. According to Bohr, atoms comprise a nucleus encircled by orbiting electrons, mirroring the celestial dance of planets around the Sun. This model, known as the solar system model, uncovers an astonishing connection between the atom and its cosmic counterpart. Both atoms and solar systems occupy infinitesimal volumes relative to the expanse they inhabit. Consider the hydrogen atom, with a diameter of approximately 0.1 nanometers, while its nucleus measures a mere 0.00001 nanometers. This remarkable disparity reveals the nucleus to be 10,000 times smaller than the atom itself. Similarly, our solar system spans roughly 287 billion kilometers, with the Sun's diameter measuring approximately 1.4 million kilometers. Astonishingly, the Sun appears 200,000 times smaller than the solar system it reigns over. In both instances, the majority of space lies unoccupied, with only microscopic particles or small bodies bustling within. And as you gaze into the depths of time, another fascinating parallel emerges. Surprisingly, both atoms and solar systems can be traced back to a shared genesis. Consider, for instance, how atoms came into existence through primordial nucleosynthesis, a process that occurred shortly after the colossal event known as the Big Bang, where protons and neutrons joined forces to forge the first elements. Similarly, solar systems took shape billions of years later, born from the gravitational collapse of vast clouds of dust and gas, which gradually coalesced to form stars and planets. However, now let us turn our attention to the grand tapestry of the universe itself. At first glance, the universe and the atom may seem worlds apart, differing greatly in scale and nature. After all, the universe encompasses the entirety of existence, while the atom represents the fundamental unit of matter with its elemental properties. Nevertheless, intriguingly, certain scholars and thinkers have drawn attention to the astonishing parallels between these seemingly disparate entities. According to a compelling theory, both the universe and the atom are composed of smaller constituents that adhere to specific patterns and principles. Consider the subatomic realm, where particles such as protons, neutrons, and electrons interact through forces like electromagnetism and gravity, shaping the intricate fabric of atoms. Similarly, on a cosmic scale, galaxies, stars, planets, and other celestial entities are intertwined through gravitational and dark energy forces, weaving a vast cosmic dance. Astonishingly, both the microcosm and the macrocosm can be elegantly described and understood through mathematical and physical frameworks. Some physicists, for instance, have postulated the existence of a unified theory, or a theory of everything that explains all natural phenomena within a single framework. This theory would merge quantum physics, which explains the behavior of matter and energy on a minuscule scale, with general relativity, which elucidates the behavior of space and time on a cosmic scale. Nonetheless, the quest for such a theory has proven arduous and elusive thus far. Though incomplete and untested, a few contenders have emerged, such as string theory or loop quantum gravity. Another hypothesis suggests that both the universe and atoms experience expansion over time. Consider how atoms can enlarge when subjected to heat, electric currents, or light stimulation. Similarly, the universe undergoes expansion propelled by dark energy, a mysterious force driving space to stretch faster than gravity can pull it back together. Atoms and the universe share a dynamic nature capable of morphing in size and form. This notion hints at potential shared causes or effects of expansion in both the microcosm and the macrocosm. Some physicists propose a connection between dark energy and quantum fluctuations of vacuum energy, minute fluctuations in energy and density within empty space that may exert a substantial impact on a larger scale. Nevertheless, this hypothesis remains imperfectly understood, with certain flaws and paradoxes, such as the cosmological constant problem and the coincidence problem. A third theory posits an intertwined origin of the universe and atoms. Just as atoms emerged through primordial nucleosynthesis following the Big Bang, where protons and neutrons joined forces to create the initial elements, the cosmos burgeoned from a singularity, an infinitely dense and scorching point that exploded, giving birth to space and time. Both atoms within the universe and the universe itself possess a traceable lineage to a shared origin. This notion argues for potential shared characteristics or patterns between the microcosm and the macrocosm. Some scientists propose a cyclic model of the universe, suggesting that it undergoes repeated cycles of expansion and contraction akin to how atoms experience cycles of excitation and relaxation. Such a model would address certain quandaries of the classic Big Bang model, such as the singularity problem and the fine-tuning problem. Nonetheless, this hypothesis lacks widespread acceptance and empirical support, presenting challenges and contradictions, such as the entropy problem and the horizon problem. And the James Webb Space Telescope has been instrumental in deepening our understanding of the Big Bang, a pivotal event that marks the universe's origin. According to the Big Bang theory, the universe ignited from a minuscule dense point and swiftly expanded. This theory posits that the early universe was incredibly compact and hot, with rapid expansion giving birth to space, time, matter, and energy. Various pieces of evidence, including cosmic microwave background radiation, elemental abundances, spatial expansion, and the formation of galaxies and stars, corroborate the Big Bang theory. Approximately 13.8 billion years ago, the universe commenced as a singularity, a point of infinite density and negligible volume within the framework of the Big Bang theory. Enveloping this singularity was the Planck epoch, a realm where the laws of physics were indistinct and inapplicable. Temperatures during this epoch exceeded a staggering 10 raised to the power of 32 Kelvin, rendering the singularity intensely hot and energetic. Subsequently, the singularity transitioned into a phase called inflation, characterized by an exceedingly brief period of exponential expansion lasting around 10 raised to the power of minus 32 seconds. During inflation, the universe underwent a staggering growth of at least 10 raised to the power of 26 in size, while temperatures and energy levels precipitously declined by multiple orders of magnitude. Inflation, besides fueling expansion, homogenized the universe, eradicating irregularities and fluctuations, resulting in a uniformly distributed and isotropic cosmos. Moreover, inflation generated minuscule quantum fluctuations that were magnified to cosmic scales, providing the foundation for the formation of cosmic structures. As inflation drew to a close, the universe entered a phase known as reheating, marked by the presence of a scorching plasma teeming with elementary particles and radiation. This plasma existed in thermal equilibrium, with all particles sharing the same temperature and energy distribution. Simultaneously, the plasma underwent rapid expansion and cooling, following the principles of the Hubble law, which dictates that the greater the spatial distance between 2 points, the faster their separation. As the cosmos expanded and cooled, it underwent a series of transformative phases, where essential characteristics underwent changes. For instance, around 10 to the power of minus 36 seconds after the Big Bang, the 4 fundamental forces of nature, gravity, electromagnetism, strong nuclear force, and weak nuclear force, separated from each other. The strong nuclear force confined quarks, the fundamental constituents of protons and neutrons, within hadrons, particles composed of quarks, approximately 10 raised to the power of minus 12 seconds after the Big Bang. Electrons, the building blocks of atoms, became electromagnetically bound to protons, positively charged hadrons, roughly 10 raised to the power of minus 6 seconds after the Big Bang, giving rise to neutral atoms of hydrogen and helium. Cooling and condensation took place in both the realm of atoms and the universe, leading to the formation of increasingly intricate structures. The expansion and cooling of the universe marked the conclusion of a period known as the Dark Ages, characterized by its darkness and opacity, devoid of stars or galaxies. The Dark Ages persisted for roughly 400 million years until gas clouds collapsed under gravitational forces, giving rise to the formation of the first stars and galaxies. The radiance emitted by these nascent celestial bodies ionized the surrounding gas, restoring transparency and enabling the observation of the universe. This significant event is known as the reionization epoch, heralding the cosmic dawn. However, the early stars and galaxies differed considerably from their present counterparts. They were notably larger, hotter, and more luminous, with significantly shorter lifespans. Through processes of nuclear fusion and supernova explosions, heavy elements such as carbon, oxygen, nitrogen, and iron were forged. These elements enriched the interstellar medium, fostering the formation of planets, the emergence of life, and the diversification of stellar types. Furthermore, the early galaxies differed from present galaxies in terms of their smaller size, more irregular shape, and greater clustering. They underwent frequent mergers and interactions, ultimately giving rise to larger and more intricate structures. Since the inception of the Big Bang, the universe has experienced continuous growth and transformation, progressing through various phases and transitions such as inflation, reheating, nucleosynthesis, recombination, dark ages, reionization, star formation, galaxy formation, structure formation, and the dominance of dark energy. At present, the cosmos is in a phase where dark energy holds sway, an enigmatic force that propels the expansion of space. The nature and behavior of dark energy hold the key to the destiny of the universe, which could lead to scenarios like the Big Freeze, the Big Rip, the Big Crunch, or the Big Bounce, a cyclic pattern of expansion and contraction. These possibilities are purely hypothetical, and one of the primary objectives of the JWST is to explore the early cosmos from the Big Bang up to approximately 1 billion years later. Equipped with its infrared capabilities, the JWST peers back over 13.5 billion years, revealing the emergence of the earliest stars and galaxies from the obscured early universe. While infrared light is imperceptible to human vision, it can penetrate dust and gas that obstructs visible light. Moreover, the JWST can observe distant objects that have been redshifted due to the expansion of space, utilizing infrared light. In its initial year of observations, the JWST has already made remarkable discoveries. It has detected some of the most remote and ancient galaxies ever observed, reaching back to a time less than 250 million years after the Big Bang. However, these galaxies, with their significant size and luminosity, challenge existing models of galaxy formation and evolution. Now, we would love to hear your thoughts on all of this. Please share your comments below.